Think it's working. We're live on YouTube, everybody. Game programming, Thursday afternoon class. I hope everybody's well and happy today. I'm going to turn my webcam around here. Let's do some yoga and some Wim Hof together, and then we'll do something. I don't know what we'll do. We can do some stuff on vectors to be kind of good. I had two other great ideas. It's a pity it's our last class because there's loads of cool stuff we could be doing. Might do a couple more videos after this, you know, because there's like one thing at least two cool things we could do that just came into my head. But anyway, we'll find something cool to do today. I think we'll learn about vectors maybe. I was thinking of something completely non-gamey that we could do, which would be interesting for our last class. Let me think. I'm going to think about it when we're doing the yoga. And by the time we're finished the yoga, I'll know whether I think it's going to be practical or not for us to do in the time that we have today. Alright, yeah, she's lovely, isn't she? Lucy is her name. Okay, cool. Let's do some yoga together, you guys. I might get a bit of music going here. Deep house instrumental. Classical focus, that sounds a bit more like it. Perfect. Alright guys, so our last yoga class of the live stream, hopefully on the internet world that we have been living in for the last year and a bit. Hopefully we'll get our vaccine soon. And next time we do yoga together, we will be in an actual classroom, so it's going to be great. Cool. Alright, hope everyone can see me. I'm going to come over here and move my camera a bit. That's better. Wonderful. Let's do a bit of programmer yoga together. So begin just allowing your head to fall all the way to the left, all the way to the right, feeling a nice stretch on the back of your neck. Looking all the way to the left, looking all the way to the right. Again, feeling a nice stretch there in the back of your neck. Looking all the way forward, rolling your head all the way back until you get to the front. Change direction and go in the opposite direction. So now take your hands, place them just below your shoulder blades, bending the knees slightly, and then roll your shoulders together so that your elbows touch, and then roll all the way back. Feeling that sort of opening now in your chest and in your back as you roll, your elbows together and go all the way back. Change direction. Cool. Stretch your arms out to the side here. We're going to bring the hands together, elbows together, and then elbows back. Elbows together, and then hands back. Oh. Every time I do this one, I can hear some cracking sounds. Very good to do this when you're sitting down for a while. Just get up and do this little stretch. And you realize just, how good it feels, how important it is. So stretching the left hand all the way out, bending the fingers of the left hand back. Other way, bending the fingers of the left hand forward now. And then try the right arm. And then we'll change direction. Then join your hands together and roll the wrists. And then change direction. I can do this in one direction, but I can't do it really very well in the other direction. Cool. Moving down the body. Stand slightly wider than shoulder width. Allow your left arm to go down the left side of your body while your right arm reaches up into the sky, wiggling your fingers. And then bring your arm all the way across, feeling a stretch on the right side of your body now. And then come back up to stand. Go the opposite way. Left arm up in the air, right arm down the right side of your body. Hands up in the air, wiggling the fingers, reaching all the way across. Very good. Coming back to stand. So now bend your knees slightly. Rotate your waist. Change direction. So now moving down the body, put your hands on your knees and rotate your knees. Change direction. Coming back to stand. Standing now on the left leg, rotating the right ankle. Change direction. Standing now on the right leg, stretching left leg out to the front, rotating your left ankle, and then change direction. Wonderful. Stretch your body out. Why don't we try, let's see, we'll try a couple of different, oh, I wonder, because it's our last class, we could try actually the sun salutation, which is quite nice. It's a little what's called a vinyasa in yoga. In other words, a sequence that sort of has a nice flow to it. It's kind of cool. This is called the sun salutation. So, just wondering, maybe I'll do it from the side. It might be easier for you guys to see. So, you can follow along or watch with me. You know, maybe you want to follow along for the first one and then join in maybe for the second one. Hey, doggy. Okay. So, yeah, it starts like this, right? And you can do this synchronized to your breath as well, and it feels really nice. But if you don't get the breath right, you can also enjoy this sequence of poses as well, right? So I'll begin. Standing like this. So it's inhale, stretch back over your head like this. Exhale, coming down to the forward bend like this. Then hands on the ground. Left leg goes back. I should really stand forward on my mat. Left leg goes back. Head up into the air like this. And then you're into the downward dog. Exhaling. From here into the cobra thing. And then back up into the downward dog. And then this leg comes forward, left leg. Big doggy. And then two hands together, hands down to the ground. And then inhaling. Hands back behind your head. Exhaling. Back to standing pose. And that's the sequence which is called the sun salutation. So I'll do it like in a kind of a flowing thing now. And you guys can maybe follow along, right? See how this goes for you. I won't do the talking this time, I'll just do the sequence. And that's one round of the sun salutation. So hopefully you guys are able to follow that alright. Try one more time. think we'll try one more of those. So let's stand, feet together, hands together. Inhale. Hey, doggy. Woo! That's 3 rounds of the downward dog. No, not the downward dog, the sun salutation. Wonderful. Let's try some Wim Hof breathing, you guys. 3 rounds. There's a new thing. Some new yoga. Come here, doggo. I think I'll turn the YouTube down a bit. Okay. Come here, doggo. Come here. Come here, ducky. Okay, so try 3 rounds of Wim Hof. So it's going to be 30 inhales and exhales, and on the last one, exhale completely and let the body do what the body does. Let's begin. Round 1. Ooh, round 1. Let's try the second round now. Let's try one more round of Hoff. So we'll begin. Wow, come back into the room, open your eyes, take a deep breath. Namaste. Alright, me and the doggy thought that was brilliant. You alright, doggy? You're so cute. Wonderful. I hope you're all well after that, you guys. I hope everybody's okay. Come back into the room. So let's do some programming stuff today. I mean, there's what should we do? I have about 10 different ideas for today's class. Like, we could do something completely out of there, like something completely non-game related, which is quite interesting and fun, or we could do vectors. Hey, you guys are all still there in the chat. Okay, I don't know, should I give you guys a chance to vote on what we should do today? Or like give me some feedback as to what you'd like to do. You're all there. Hey, good, you're all still there. Cool. I'm just like not too sure what to do with you guys because it is our last class. Should we do something like relevant and gamesy, or should we do something completely out there, like something different altogether? Vectors. Okay, vectors it is. Alrighty, I can see coming up in the chat. Vectors it is. Okay, cool. We'll do vectors. Vectors are actually kind of cool and relevant and important to you guys There's loads of stuff though. So many cool stuff. I'd like to teach you guys a class on strings, but it'll have to wait. I can't believe it's our last class, you know. No, we're kind of fine. Pathfinding. You want to learn about pathfinding? Any like basic code that would relate to yeah, you kind of all want to know about making games and stuff. Pathfinding. Do you want to know? We could do pathfinding in Unity as well. There'd be kind of a good chance to play with the navigation graph, the nav mesh. I haven't prepared the nav mesh thing, but I actually need to teach it in my 4th year class tomorrow as well. We could have a crack at it. And I'm definitely not going to share this live stream afterwards, like publicly, because I haven't really prepared anything for it. So, Gabriel wants to know about pathfinding, which is using the nav mesh in Unity. Vectors is kind of cool too. Physics is really cool. You're going to do lots of this stuff like next year as well. I'll have to decide something soon, because otherwise the class will be over and we won't have learned anything new. Okay, I'll teach you guys about vectors. Alright, because vectors are quite important. It's no harm that you get used to, like, you know, knowing a little bit of how vectors work. By the way, the study of vectors, okay, vectors it is. I wanted to do something like mind-blowing with you on the last class. Vectors are not that mind-blowing. Is there anything mind-blowing you can do with vectors? Dot product, cross product is kind of fun. Pathfinding is kind of fun. Okay, we'll do vectors, right? Because like okay, vectors. Okay, cool. I'm going to start up the whiteboard here, because this is how we're going to do the vectors thing. Here is my whiteboard here. Okay, cool. So here's the theory behind vectors and everything that you need to know about vectors, okay? Vectors. Okay, so what we need to know about vectors. We need to know what is a vector. What is? Then you need to know about the operations that you can do on vectors, which are adding vectors, subtracting vectors, multiplying a vector by a scalar, multiplying a vector by another vector. And there's actually 3 ways to multiply vectors together. So we've got add, subtracting. We also have the concept of normalizing a vector. Normalizing, and we have the concept of the length of a vector as well. L-E-N-G-T-H, the length of a vector. Okay, cool. We'll start out with what is a vector. All right. Lots of quantities in computer games can be represented by a single number. But then there are lots of quantities in computer games that require multiple numbers. And the sort of like technical definition for a vector is simply a list of numbers. It's a list of numbers. And the list of numbers kind of obeys certain rules. The first thing that we could use vectors... Am I not screen sharing? Sorry, you guys. I thought I was screen sharing. Thank you. Here we go. The vector is a list of numbers. That's what I had previously written on the whiteboard there. It's a list of numbers. You can add them, you can subtract them, you can multiply them in 3 different ways, which we'll talk about. You can normalize the vector and you can get the length of a vector as well. So what is a vector? A vector is a list of numbers. In Unity, a vector is encapsulated into a thing called a vector 3 or a vector 2. And these types of vectors, the list of numbers actually have variable names as well. In these things here, for vector 3s and vector 2s, they're called x, y, and z if it's a vector 3. In processing, there's a class called a p-vector. And a p-vector similarly has got like x, y, and z components on it. And it also has methods to do all of these things, like adding, subtracting, multiplying, normalizing, and calculating the length. In Unity, because we're using C#, this is using the C# language, doing vectors in Unity is actually easier than doing vectors in processing. because C# supports a feature called operator overloading, which means when you're adding C# vectors, you can just use the plus symbol, and you can use the minus symbol for subtracting them, and the multiply by symbol for multiplying them. With a P vector in processing, you have to actually call methods like .add, and that's because this is based on the Java programming language. That's what processing is based on. So we're adding, subtracting vectors and so on, using, like I say, the operators in C# and using methods in Java. So we've got P vectors like that. So that's what the vector is, right? That's what a vector is like in code. Let's say we want to talk about what exactly a vector is. Say we're in the processing world, right? And say in the processing world we have, well, actually it doesn't really matter. We'll do it in the Unity world. If we're in the Unity world, say we have, this is the x-axis like this, and this is, we'll say, the y-axis over here. So we can represent any position using, distance from the y-axis and distance from the x-axis. So say I picked this position here, and if this position was, say, over 2 and down, we'll say 8. Okay, so this is the position of, we'll say, some little object in a scene like this, right? And on one frame, its position is over 2 and up 8 from the x-axis. That's its kind of position. We'll say on the next frame, it has moved to a new position. We'll say it has moved to this position here, which is going to be over 5 and down 8. So this is at point, we'll say t0, and this is at point, this should really be t with a lowercase t. This is at time t0, and this is at time t1. So, what do I mean here by t0 and t1? I just mean one frame, the thing is located at position 2, 8, and then the next frame, the thing is located at position 5, 8. Does that make sense for everybody? You just draw it here at one frame, and then you draw it here at the next frame, and you see that this thing has moved this amount from one frame to the next. Now, the distance that this thing has moved is given by, we'll say this is A and this is B, and by the way, if these were written in maths, that you'd write a little line over that to say it's a vector, and this is the B vector here, and these are positions. So this is A, so A's position is 2, 8, and B, the position is 5 and 8, and this is at frame 0 and this is frame 1. So between this frame and this frame, the x component has changed by 3, hasn't it? So it's gone from 2 to 5, so 3 has been added to the x component. And what's been added to the y component? Nothing has been added to the y component. So we get this thing here. We get this other vector, which we can call c, for example. Now, how did I calculate c? It's very simple. I subtracted the x's from b from the x's from a, and that gave me the x of c. And I subtracted the y of b from the y of a, and that gave me this value of 0 here. So what we can say then is the vector c is going to be equals to the vector b minus the vector a. Does that make sense for everybody? That is subtracting one vector from another. And when you subtract one vector from another, yeah, each vector controls the x, y, and z. Each vector in here is x and y. Alright, so this is x is 2 and then the y is 8. Over here the x is 5 and the y is 8. So we can see if this is basically the same thing on one frame, and then the next frame it's here. I've got two position vectors that control the positions, and you can see that you can calculate the difference between them by subtracting the x's and subtracting the y's one from another. So this is the subtraction operation for vectors. It means subtracting the x's and subtracting the y's from each other. So you can rewrite this, because this is because we said subtracting. You can also rewrite this. You can say that b is equals to a plus c. So that makes sense as well. You take the vector c. If you take the vector c, which is 3, 0, and you add it to the vector a, which is 2, 8, you get the vector b, which is 5, 8. Does that make sense for everybody? Vector 2 and vector 3. A vector 2 just has, Declan says, what's the difference between a vector 2 and a vector 3? A vector 2 is used for 2D, and it just has x and y. A vector 3 is for 3D, and it has x, y, and it also has a z value as well. That's the difference between them. So this is the first thing we learn about vectors, that you can add vectors together and subtract vectors together by adding the x components of the vector to the y components of the vector. So, cool. All right, that's adding vectors and subtracting vectors. Is that cool for everybody? Adding and subtracting vectors means adding the x's and subtracting the x's from another, and then you end up with this thing here. Now, let me redraw this thing over here, okay? And then we'll talk about some other properties of vectors. Here's my x-axis again. Say again my a's, or my value here, my starting position is going to be like over 5 and down, let's say 6. And say in the next frame it is moved to here, so this is going to be like over 10, and we'll say down 11. Alright, so this is the same object. It's here one frame, and then the next frame it's over here. So we see that it has moved a total of like 5 and 5. Alright, so this is, if this is A, this is B, this is C, and I can say that B equals A plus C, or similarly you can say C equals B minus A. C equals B minus A. So these are like the operations on vectors, adding vectors, subtracting vectors. Alrighty, cool. So the next thing we might be curious to know is like how far has A traveled when it reached B? So you can see that like it's traveled 5 units this way and 5 units up to this way to reach B, but it doesn't actually travel 10 units. Of course it doesn't, because it's traveling the straight line distance between A and B, and that's the straight line distance between A and B. And this is the vector 5, 5. This is the, moving 5 units in this way, 5 units in this way, and you see, of course, you end up with a right angle triangle here. So you got 5 and 5 here. You end up with a right angle triangle here. And so we have this vector 5, 5, and I want to know what is the length of this. Well, obviously, because of Pythagoras, that is going to be the square root of 5 squared plus 5 squared. And this thing here can be rewritten as the square root of x squared plus y squared for a vector. And if, x squared is the x component of the vector, y is the y component of the vector, and you get the square root of them. So 5 squared plus 5 squared, so that's going to be like 25 plus 25, so it's going to be the square root of 50 in this example here. I don't know what the square root of 50 is, we'd have to probably type it into our calculator, but that will give you the exact distance that's traveled across here. And hopefully you can see from this diagram like how you would actually calculate this distance and why it's like the square root of the x component plus the y component. So what is the relevance of all of this? If you can see that A has moved to B, and it's moved to B by adding C between A and B, or adding C to A, the total distance traveled is going to be the square root of, this vector here, which is the C vector. And this property of a vector is called the magnitude of a vector, the magnitude. It's called the magnitude, also known as the length of the vector, L-E-N-G-T-H, right? Yeah, so the magnitude of the vector or the length of the vector. Hey, it's also worth thinking, like, what is the origin of the vector? Where does this vector start? Like, this vector A clearly starts here. It goes all the way to here. This vector B is all the way over here. So that starts at the origin, and you count out from the origin. So that's the direction of the vector. This vector C similarly has this direction here, and it starts at A. So it starts at A and goes to B, and it has this direction here. Anyway, when you do this thing here, this is called calculating the magnitude or the length of the vector. So that's what that means there. Okay, so that's the magnitude of a vector. Next property of a vector. Sometimes I might want to know in what direction a vector is pointing, but I don't really care about the magnitude of it, right? Again, if we take this diagram here, and we got vector A, and we got vector B over here, so we got vector A and vector B. A is moving towards B in this direction here, and I want to know what direction is the vector, but I don't really care like how far it is. I'll tell you why. A classic example of this would be if you said that A wants to move towards B at a particular speed. I want it to move at like 3 units per second. Then I would want to know what is 1 unit, and then I'm going to multiply by the time. So what 1 unit is basically the vector that brings me from A to B. Again, let's put numbers in here. Let's say this is, what did I say this one was? 5, 6, and then 10, 11. Say this is the vector 5, 6. And this is the vector 10, 11. You know what, we'll code this up in Unity and I'll show you what all this stuff looks like in Unity as well. We'll make these vectors A and B and we'll place things at these positions. And I want to move A towards B at, we'll say, 3 units per second. Then I need to know, like, what exactly is 1 unit? You know, if I'm moving at 3 units per second, then I want to move, like, you know, if the distance here is 3, then it's going to take 1 second to get from A to B. So you might want to know, like, what is the direction? You know, what is 1 unit towards B? So, actually, you know what? It's slightly easier to visualize this if these guys were kind of vertical. Let's say A again, let's pick this one here. What did I say it was? Let's say it's over 5 and down 6. And let's say the next frame B is all the way up here. And let's say this is also over 5. And this time it's down 10 like that. This is just a little bit easier to visualize, right? So I can see that the distance between those two vectors is 5. All right, because I've got to go. Oh no, sorry, it's 4. It's 4. My computer's running weirdly today. The Z is not working. So the distance from here to here is going to be 4. So to go from 6, and then that's going to be 10. The distance from here to here is going to be 4. There we go. So to go from A to B is going to be 4 units. So what is 1 unit? So say for example, I want to travel at 2 units per second. So at 2 units per second, and that means I'm going to go here, and I know that the distance is 4. So that means after 1 second I'm going to be here, and after 2 seconds I'm going to be here. So I need to know, like, where am I going to be? Like, what is 1 unit towards 1 unit between A and B? 1 unit towards A and B is quite clearly 1 and 0. Because if you keep adding, sorry, not 1 and 0, it's going to be 0 and 1. Because if you keep adding 0 and 1 to 5 and 6, eventually you're going to get to 5 and 10. How did I calculate this 0 and 1 thing here? The actual formula for calculating this is very straightforward. Like I'll show you. It's called normalizing a vector. And it's the thing of normalizing the vector, right? Let me show you. Normalizing. So normalizing a vector means you take the x and y components of the vector and you divide each component of the vector by what's called, say if A is equals to the vector A and B, or x and y, you divide by the length of A. And in vectors, the length of a vector is written, or the magnitude of a vector is written as 2 pipe symbols, 1 pipe symbol here and 1 pipe symbol here. These are like straight lines. So this is called the length of a vector. So let's look at this example and see how this would actually work. And then I think we'll switch over into Unity. We'll write some code because like all this stuff is very theoretical at the moment. I'll show you how you actually use all this stuff, right? So I'm here at 5 and 6. I want to go to 5 and 10. What is the length of the vector that brings me from A to B? So we'll say C equals B minus A. So C then is going to be equals to the vector 0 and 4. And the length of that vector, the magnitude of it, is going to be equals to, I'll write this over here. The magnitude of this vector is going to be equals to the square root of 0 squared plus 4 squared. 4 squared is 16, so that is going to be value of 4. And of course you know that it's going to be 4. Like to go from 5, 6 to 5, 10, you have to travel 4 units. You can see that from this. And this is just basically how it's calculated. So back to this thing of the normalizing a vector thing here. If you take, this is the formula for normalizing a vector. If you take the vector, like let's see, our vector here was 0, 4. And we divide by the length of the vector, which is basically 4. So we take 4 into 0 goes 0. And then 4 into 4 goes 1. So you end up with the vector 0 and 1, which is exactly what you'd imagine. And this thing of normalizing a vector, what this actually means is it means making a vector of length 1. Like I say, to normalize a vector in Unity, you just call dot normalize. And you basically, what's happening there is it's going to divide each element of the vector by the length of that vector. So that's what normalizing a vector is. I think we'll switch over into Unity now. We'll kind of like, I'll show you how all of this kind of like might work in code. Unity is the best for this. I'm trying to think, should we do this in Unity? I might show you in processing as well. Unity is kind of nice because you're going to be doing Unity. Processing is kind of good because you don't have the Unity editor. You got to draw the thing. So we'll do Unity, and I might have to do a processing example as well, right? Let me see. Do I have a Unity project for you guys? Open project. Documents. Hello Unity. Projects. Thanks to merging cubes. I'll just use this Hello Unity project here. There's nothing important in it. I'll share it after the class. Oh, here, this will do here. I'm starting a new Unity project there, but it's taking, oh, come on, it's new scene, basic. Here we go. Alrighty. So I got a new scene here in Unity. Let's do some things with vectors in this new scene. Let me make sure the chat is running in the other window there in case people want to ask me questions. Gotcha. Live stream. Okay, cool. Here's the Unity thing, right? Let me create a couple of game objects here. Let me create a quad first of all, so we can make a little world. Let's say the position of the quad is 0, 0, 0. Let's make the quad rotate 90 degrees like this, and then let's drop some green. Yeah, do stuff on 2D games. To be honest with you, I'm actually not very familiar with Unity 2D. I've actually never used Unity 2D. Can you use a vector 3D? Oh yeah, you can use a vector 3D in some cases for sure. Lots of times you want to use vector 3s for different things. You can use vector 3s for lots of things, like even colors and stuff can be stored in a vector 3. Okay, there's my quad. Let's make the quad big. Dragging green onto the quad. There we go. Let's make a couple of things in here. Let me go create a 3D object. I'm going to create spheres. I'm going to assign that to be the value of 0, 0, 0. There's a sphere. Actually, let me not make it a sphere. No, actually, sphere is fine. Yeah, I'm just trying to think, is it better to make them something that have direction? Maybe it is better to make them something that have directions. I think I'm going to make a 3D object. I'm going to make a cube instead. Yeah. And I'm going to set the Z value of the cube to be 2. And set its position to be 0, 0.5, and 0. So there's the cube there. I'm going to maybe make that a different color, so you can see it. There's blue. Drag blue onto the cube. There we go. Look at it from above. Let's see the cube from above. There's the cube sitting on the thing. Let's give the cube a destination, a sphere. So let's make a 3D object for this. Let's make a sphere. And I'll drop you somewhere else, Mr. Sphere, so that I can make this cube thing move towards the sphere maybe. Yeah, that's a good plan. There's the sphere. Let's make the sphere red. This is going to work out, you guys. We're going to learn some good, useful stuff here. Okay, here we go. There's the sphere dropped on. And so now I have this cube here and I have this sphere. Guys, if you have Unity open, you can follow along, code along. We're not going to type too much code today. Anyway, here we go. Here's a sphere and here's a cube. Alrighty. So, you know what? Let's do a few things first of all. Let's make the sphere, like, let's put it on the 0 and the X as well. So it's on the same, like, you know, it's forward. Basically, if it's the Z, I'm going to say it's to be 10. Okay, so it's basically 0, 0.5, and 10. And then the cube is 0, 0.5, and 0. Alright, so that's basically the scene that I got set up here. Now I'll show you how to use vectors. Okay, how we can use vectors to do certain calculations. Here is the cube. Right, I'm going to click Add Script to the cube Add component. and I'm going to call this vector test. New script, create an add. So there we go. Let me edit the vector test script now. So let me click edit script. Here's vector test. All right, you guys, I'm gonna, hopefully you remember this, I'm gonna make a public field here. Public transform, let's make this the target. And that should be transform with an uppercase T. So, okay, so basically, because this is public, you can, in Unity, you can take the cube thingy and you can drag the sphere onto that public target field here. Hey, somebody at the door. Hello. I'm on my live stream for my class.
They can't see me.
No.
Good.
Can I take the doggy? Okay, cool. Okay, I'm back. Here we go. Alright, so basically the cube and the sphere. Here's the sphere. Here's the cube. We got a script going on the cube here. Oh yeah, and I've dragged the sphere as the target for the cube. So let me click on the vector test C# code. Yeah, here we go. We're back in the C# code now. So I've got the transform here for the target. Okay. So I want to just demonstrate those things that I showed you, adding vectors, subtracting vectors, and so on. Like looking at this scenario here, you can quite clearly see that the cube is 10 units behind the sphere. All right, because the sphere is located at 0, 0.5, and 10, and then the cube is 0, 0.5, and 0. So the sphere is 10 units in front. Okay, so the first thing it can do is test out this vector addition and subtraction thing here. Let's go this vector 3. Vector 3, let's call this 2 sphere. So the 2 sphere vector is going to be equals to transform dot position. No, it's going to be the target dot position minus transform dot position. Okay, so that gives me the vector that if I was to add it to my position straight away, I would immediately become the sphere. So I'll just show you what that value is, and then we can do debug dot log the 2 sphere vector. And obviously that 2 sphere vector is going to have the value of 0 and 10. Okay, cool. All right, let's check it out. See what happens. Alt tab. This is going to be probably the least exciting Unity program you're ever going to write. Hitting the play button. And there we go. The vector is 0, 0, and zooming in there. There's your vector 0, 0, and 10. Okay, so that is subtracting one vector from another vector. Watch what happens if I add those vectors together. Now I have the 2 sphere vector. If I then add the 2 sphere vector to me, that's going to make me immediately equal to the position of the sphere. So if I go transform that position plus equals to the 2 sphere vector, watch what happens. So this is adding and subtracting vectors together. Hitting the play button. So now the cube and the sphere are going to have the same position, right? Because I've just taken the thing that's going to bring me to the sphere and I've added it to my position. So now the position of the cube becomes the same position as the sphere. So that's adding and subtracting vectors. Now maybe I want to know how far is it to the target. So there's 2 ways in Unity that you can do that. The first way you can do that is by calculating the magnitude or the length of the 2 sphere vector. So I can go debug dot log 2 sphere dot magnitude. So that gives me the length of a vector like that. 2 sphere dot magnitude tells me if we are, if that's the length of the vector. Gives me the distance. So actually, you know what we can do here? Let's put this into update. So we can see it getting printed out every frame. Saving there, jumping back over to here. Here's my console, undoing, maximize on play, hitting the play button now. And there it is, it's 10. And notice, like, if I take the cube and I bring it closer, that value is going to reduce. You can see that the value now is like getting smaller as I bring the cube towards the sphere. So that is what the magnitude of a vector means, right? The magnitude of a vector means so you get the length of the vector, and you know we looked at how that's calculated. The square root of the x is to be squared, and the square roots of the y is to be squared. Another way you can do this in Unity is by going vector3 dot distance. So you can pass in two vectors. So you can go target dot position, comma. Let's see, does it know? Not the two sphere vector. Transform dot position. So this will do the same thing. You know, this is another way to calculate like the distance between those two position vectors. So you can use vector3 dot distance, or you can subtract one vector from another, and then you can get the magnitude of that resulting vector. Oh yeah, we don't need to save it. So hitting the play button now, you'll see that those two values should be the same. So yeah, there we go. It's printed out 10. And then if I take the cube and I drag the cube around a little bit, you can see that the cube is, yeah, it's the same thing. Okay, you guys, if you are coding along, I need to step out for about 2 seconds. Maybe maybe slightly longer than that. Maybe like half a minute or a minute. You guys can just see if you can write some code, like an application for even this simple thing would be a simple like little AI, right? Say you have this little thing here, and maybe it's got two states. Maybe it has like an idle state and it has an attack state or whatever. And you want it to switch between its idle state and the attack state if this guy comes inside the range. So we'll say the range is like 5 in this example here. So I want to basically say, am I idle or am I attack? And if this guy is within 5 units of this guy, we're going to print attack. Otherwise, we're going to print idle. Can you guys see if you can code that? It should be very simple, and I'll be right back. Cool, I'm back. Have you got it, you guys? So, again, like I say, this is just a quick example of, you know, even this basic like vector stuff, how you can use it. So, here we go. Here's the two sphere vector. We're getting the magnitude of it. You can also do the same thing by using dot distance on the vector 3, and that gives you the distance between the two vectors. So, like, I could say something like this. You guys have it. I'm sure it's pretty straightforward. You know, if, like, we can do it both ways. Two sphere dot magnitude, we'll say is less than 5. You could say if the magnitude is less than 5, we're going to go debug dot log. We're in the idle state. else we're going to be in the attack state. There you go. Simple as that. All right, let's just test that out. What? Where is that getting printed out? Let me stop printing out those magnitude things. Oh yeah, I forgot to save it as well. Okay, here we go. So, are we in the attack state? I thought we were a bit farther away than that. Magnitude is less than 5. Oh, it should be the other way around. It's greater than 5. In other words, if we're greater than 5 units away, we're going to be in the... Yeah, thanks, Tranquil Shine, you're dead right. Should be the other way around. So we're in the idle thingy, and then if the evil sphere comes within range of the blue is going to switch to the attack thing. You can see we're using vectors there to, basically to evaluate the distance between those things using what's called linear algebra or vector arithmetic by getting the magnitude of the vector that brings me from the cube to the sphere. Cool. So there we go. That's the magnitude of a vector. Okay, so the next thing is normalizing the vector, and what does that mean and why would you want to calculate it, right? So let's basically say cool, let's do this then, right? Let's go vector 3 n for the normalized version is going to be equals to 2 sphere dot normalized. So this is how you normalize a vector, right? This basically returns the normalized version of 2 sphere into the vector n. It returns this vector with a magnitude of 1. Yeah, this doesn't. Yeah, cool. It doesn't. You can also go 2 sphere dot normalize. There's actually, I'm going to show you the 3 ways you can do this. 2 sphere dot normalize, you can call that. That normalizes the 2 sphere vector. The first one doesn't actually change the value of the 2 sphere vector. I'll just say this. This doesn't change 2 sphere, but just returns a normal version of the 2 sphere vector. This one actually normalizes 2 sphere. Changes 2 sphere, I'll just say. The other way you can do it is actually you can use a vector 3. F11, you can use vector 3, VECTOR3, dot normalize, and this is what's called a static method, but you can pass in a vector n and it returns you a new vector, which is the normalized version of the vector n. So actually, again, you can use like 2 sphere. There's just 3 different ways of normalizing a vector in Unity. And you can go n equals vector 3 dot normalize. So they all normalize the vector and return it in different ways. Let's print out the value of n and see what it looks like. Debug.log. Okay, cool. So there we go. We're just going to print out the value of n and see what it looks like. So let's jump back over here into Unity. This is the example we're working on here. So if I hit play now, check out the value of n. It's going to be the vector 0, 0, 1 anyway, because these are basically vertically aligned to each other, right? And if you zoom in there, you'll see on the console, that's the vector 0, 0, 1. That's the normalized version of the vector that brings me from the blue thing to the red thing. So similar, like it doesn't really matter. If you take this cube, this sphere, it doesn't matter where you drag it to. -1 if it's behind it, +1 if it's in front of it, and then see what happens if you drag it over here. Now it's actually changing its value to be like 0.6, 0, and 0.8. So it's still a point on what's called the unit sphere. It's always of length 1, no matter where you drag it to. So what's the purpose of normalizing this vector? I'm going to show you two applications for normalizing the vector. Okay, there's some. It's just like I'm just thinking of two off the top of my head, like why you would want to normalize the vector, right? Check this out. Here's vector test, right? Say I wanted this game object to point. Say I wanted the blue cube thingy to point at the red sphere. I want it basically to be angled so that it's looking at the red sphere. Well, one way you can do that is by assigning the forward vector of the blue cube. So I'll show you what that looks like. You know, the transform has got vectors built into it already. It has like a vector for position, it has a vector for forward, it has a vector for right, and it has a vector for up. So if you just did something like this, transform dot forward equals n. Look at that. What's going to happen here? So this is going to say my forward vector, or the forward vector for this blue thing, is now this normalized vector that we've just calculated. So if you hit play now, watch what happens. If I drag this thing over here, look at this. The blue thing magically follows the red thing now, because I'm assigning its forward vector. I'm saying it's kind of like forward vector is the direction of it. You know, I'm basically saying it's forward vector, and that works like whether you bring it up in the air or down, whatever. Up there, it's still always going to point at it like that. So that's a use for that normalized vector. It's interesting here that even if you just assign it to be the two sphere vector, even though it's not normalized, it will still work, and Unity will actually normalize it for you. There we go. So it will still work. So that's one application for like normalizing a vector. Another, yeah, exactly, it will do, because it's just doing like the position of the target minus the position of the cube thingy. And so it's subtracting the x's and subtracting the y's and subtracting the z's. By the way, another way you can do this, just to show you, like this is one way. There's like often in Unity, like there's you know lots of different ways to achieve the same goal. Another way to achieve the same goal is to actually use this method. So you can go transform.lookat, and this does the same thing, right? So you just transform.lookat, we call it the target. So this will do exactly the same thing, right? These are identical. So this will do the same thing. I'll just show you. So if I save that, jump back over here into Unity, hit the play button, I see it achieves the same thing, right? The transform.lookat is basically doing that calculation for you in a method in Unity, but it will do exactly the same thing. So it makes one game object look at another game object. We've done it with vectors. You could also do it using transform.lookat. So the next thing, right? Say I want to, like, there's typically many ways to do this, right? If I want this cube to move towards the sphere, I want it to move towards the sphere at a certain speed. Well, how would we do that? So let's using vectors. Yeah, they all work in 2D. You can normalize a 2D vector, and you can also yeah, calculate the plus and minus of 2D vectors as well. All work really well in 2D or 3D. Okay, here's my cube, right? I want my cube to move at a certain speed towards the sphere. Actually, we'll do this a few ways around. We'll be able to say travel towards the sphere at a certain speed. Let's do that first of all, right? Let's say here's the cube. We've got vector test. Go back over here into Unity. There's the target. Let me make a public vector 3 or public float for speed. Let's say my speed is going to be 1. So I'm going to move towards the target at a speed of 1 unit every second. This is the speed in units per second. Now, we have all this code here. There's actually there's several ways we could do this. Of course, you can do this. Method number 1, transform.translate. Okay, and I'll show you how to do this with vectors as well. You can do transform.translate 0 to 0, and then you can take speed. Oh, yeah, tab 9 is doing the code completion for me. You can do speed multiplied by time. This will obviously do it. This is not using vectors. Let's just see how this works. Make sure that it works. This is going to take 10. This is going to take 10 seconds because I've specified my speed as being 1. There's vector test. Speed is 1. So there it goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there it goes. Transform.translate. So it's going to take 10 seconds. Another way we could write this is using vectors. And if we're using vectors, then we could do it like this. Transform. Let's go here. Vector 3 pause. This is going to be the new pause. Is going to be equals to transform.position plus the speed multiplied by time in the direction towards the sphere. So n multiplied by speed multiplied by time. So this is like I say using vectors. Cool. So we're not even doing the rotation. Let's not even do the rotation. So you can just see it calculates the vector that's going to bring you from the blue cube to the red sphere, and then what it's doing is it is normalizing it, and then we're taking the normalized vector multiplied by the speed that we're traveling multiplied by the time. So this is multiplying a vector by a scalar, by the way. It's called scaling a vector. So this vector n is of length 1, and then you multiply by the speed, which is going to be 1, and then you multiply by the time. And this gives you moving from the cube starting position towards the sphere at a particular speed. And it doesn't matter whether the cube is looking at the sphere or not looking at the sphere. Let's check it out. Here we go, hitting the play button now. We're going to travel towards the blue cube is going to travel towards the sphere. Oh, hang on, I haven't quite worked that one out. New pause, and then we need to go transform dot position equals new pause. So that's using vectors. There we go. So now I'm moving 10 units from the blue cube. I'm moving at a speed of 10. It's still going to take me, because, oh no, the distance is now no longer 10. The distance is some other value. So I'm going to travel at 10 units every, I'm going to travel basically at 1 unit every frame, towards this thing here. Now, okay, I hope you've kind of got the whole gist of this so far, all right? So we're adding vectors, subtracting vectors, normalizing a vector, calculating the magnitude of a vector, which is the same as subtracting, same as the distance between two position vectors. This thing here is multiplying a vector by a scalar. I just maybe want to explore that a little bit. All that's happening here is it basically takes the x components multiplied by this value and the y components multiplied by this value as well. So how would we rewrite this so that I say take exactly 10 seconds? Let's do this. Public float time. Let's say the time is going to be equals to 10. So I want to take exactly 10 seconds now. No matter what the distance is, I want to take exactly 10 seconds for this blue cube to get to the red sphere. So I'm going to just do my whiteboard thing for this. Because I want to just write a little note here. We have this little equation of motion, which is distance equals speed multiplied by time. And now in this one here, we're given time, and I also can calculate the distance. Now I need to calculate the speed, because I want to travel and I want to take exactly 10 seconds for the blue cube to reach the red sphere. So now what I need to do to work this out is like, what does the speed need to be? Well, I basically want to get speed on one side and everything else on the other side. So it's actually just distance over time gives you the speed. So that's how we will write this. Take exactly 10 seconds. So if the time is that, then let's say distance is going to be equals to vector 3 dot distance, target dot transform dot position and transform position. Nice one. It's written that for me. So then speed is going to be equals to distance. Oh, look at that. It predicted divided by time. Fabulous. Speed equals distance divided by time. So, cool. So now it's going to take exactly 10 seconds for the blue cube to reach the red sphere. And look what's actually happened with the cube here. It said that the speed is 1.2, so 1.2 units every second. We've calculated the direction vector by subtracting this guy's position from this guy's position and normalizing it. So now we know, like, you know, in what direction do we need to travel. And we got speed and time. So hopefully you can see how these vector things kind of like all relate. These vector ideas of vectors and you know, distance and subtracting vectors, adding vectors, multiplying vectors by scalars, normalizing vectors, and calculating the magnitude or the length of a vector. Maybe I'll show you one last thing in vectors, right? And then you guys are up to speed on vectors, so to speak. One last thing on vectors is actually kind of, I don't know, this is quite interesting, right? Say you had a couple of agents in a game, right? And you wanted to implement some AI. Say you had this guy over here. And this guy was looking over in this direction here. And this guy is basically your, well, say this guy is some NPC, right? And say this NPC has got an AI. And I want this NPC to know if an enemy comes in range, okay? So if the enemy comes in range, we might have two rules for what does that mean if the enemy comes in range. Here's my enemy over here. And then we'll see how we can solve this problem using vectors, right? Now, say that the enemy comes in range in two conditions. Number one, if the distance is less than 5, then it's kind of like in range. And then the other rule, we might say if it's inside the field of view. If it's inside the field of view, right? So what's my field of view? Yeah, exactly, like their cone of vision, right? So we can do that. Like basically draw a little line over here. I'm going to use different pen color for this. Say I make this in green. Come on, green pen. Is green pen working? No. Green pen, fabulous. Green pen is working now, right? Here's my cone of vision, right? So I have this 45-degree field of view. We'll say it's like 45 degrees here and 45 degrees here. So there's basically an angle here and an angle here. Okay, and you can see this enemy. I want to know, is the enemy inside the field of view and if the distance is whatever and so on. Okay, so you can kind of see what this problem is going to be, right? This problem is going to be two parts. The distance bit is easy because we can just get the distance between them. The field of view part, what we actually need to do is calculate this angle here. That should be along the center line. It's quite challenging to draw. We need to calculate this angle here, theta. And we need to say if theta is less than 45 degrees, then I know it's inside the field of view. Otherwise, it's outside the field of view. Does that make sense for everybody? So it's a field of view calculation. You can see here if this little enemy dude, change pen, everything is screwing up for me today. If the enemy was here, then the angle would be this angle here. And it'd be inside the field of view. But the enemy's over here, so it's outside the field of view. So we want to go inside the field of view, outside the field of view. How do we do this using vectors? Okay, well, I'm going to show you two ways. The easy way and the hard way. The hard way is how computer scientists would probably attempt this. The easy way is how a Unity programmer would do this. First way is this, right? And this is the cool way. This is the kind of cool way, but it's a bit more complicated. And then I will show you like the simple way, because like you can basically do this in one line in Unity. If you have two vectors here, let me redraw this in black. Say you have, this is my thing here, and you have this vector A over here, and you have this vector B over here. And you take this line that goes from the origin. Wow, this whiteboard thing is so slow today. So you got this vector B, and you've got this vector A. Okay. A very curious property of these vectors, which you can derive if you draw some diagrams and things, is this angle here, which is the angle between those two vectors, right? The angle between those two vectors is given by a very, very interesting little formula. And here's the formula for calculating the angle between two vectors, right? Theta in this example here, which is the angle between A and B. If you take the vector A and you multiply it by the vector B by using a special type of multiplication called the dot product. The dot product very simply means that you just multiply the x's together and you multiply the y's of the vector together. And then you divide that by the length of A times the length of B. And you take all of that stuff, right? Now theta's not quite into... how do I copy and paste here? Can I chop this bit off? I need a bit more room because I actually haven't written the formula properly. Lasso select, add note, lasso select, let me try lasso select, this thing, ooh, can I move it? Very good, move it over there, cool, we're back to this thing. Oh no, I don't want lasso select, I want this pen, cos -1. Everybody, when you come to learn, when you come to study, if you wanted to take my subject in third year, this is something that we learn in about like week 1 or week 2, this formula here. Theta, which is the angle between two vectors, is equals to the inverse cosine of the dot product of A with B over the length of A times the length of B. This little formula here allows you to calculate the angle between two vectors. How would we write this in code? And then I'll show you. Like, this is just something that you learn. It's basically the angle between two vectors is given by this formula here. A dotted with B over the length of A vector times the length of B vector. Don't forget, if the A vector and the B vector are normals, if they're of length 1, then you just divide by nothing, because anything divided by 1 is itself. So this little formula here can calculate the angle between two vectors. Now, if we go over to this little problem that we were trying to solve earlier, which is the field of view calculation, let's see what are we calculating the distance, what are we calculating angles between and what. And we could get another little bit of space over here. This whiteboard is getting very cluttered. I should sell this as one of those non-fungible token things by the end of this class as a digital artifact. This is all the diagrams I've drawn for all my subjects since the start of this semester. Well, since I discovered this whiteboard thing. Here's the problem again, right? Here's A with its little field of view thingy going on over here. Oops. And here's B over here. And I want to know if A is inside the field of view of B or not inside the field of view. So what we would do to calculate this angle between A to B over here, this guy here, this angle here is what we basically want to calculate. This is the dot product between the vector B minus A and the forward vector of A. So the forward vector of A, so A dot forward, I'll just put A dot forward. Hopefully you can see that from the diagram. The vector B minus A is this vector here. Now the vector that brings you from A to B. And then A dot forward is the vector that's pointing out of A in the straightforward direction. So like if this angle between, you know, the forward vector of A and the B minus A vector, if that's less than 45 degrees, we're inside the field of view. If it's greater than 45 degrees, we're outside the field of view. I hope the diagram kind of makes sense for you guys. I'll show you what it looks like in code now, right? So here's a vector test, right? So now I have the target thingy and I have my own vector, and then let's do the field of view calculation, right? Let's go here. First of all, float theta, which is going to be the angle that I'm checking. Theta is going to be equals to the a cos, and then to get a cos, it's mathf dot a cos, the inverse cosine of which vectors? It's going to be the what do they call it? Two sphere vector. Yep. Dot normalized, or you can divide by. We'll just do the divide by the two sphere and transform dot forward. Oh, hang on here, there's loads more to this. It's going to be the inverse cosine of the dot product. The dot product of two vectors you get with vector 3 dot dot. So we want to get the dot product of those two vectors divided by the length of the two sphere vector, because the length of the transform dot forward is 1. So that's how you would write that code in Unity, and then you close this thing here. Now, yeah, cool. This value that we're going to get out here is in fact going to be in radians. Nice. That's the formula. Everybody, I'll just show you this again because it's kind of worth like just noting. Here we go. A's forward vector is this. There's the vector that brings you from A to B, and you get that by going B minus A. So we're getting, and let's look at the formula again. The formula is probably all the way over here. I'll just write it one more time for you guys. The angle here, theta angle, is going to be equals to the inverse cosine, the A cos of A dotted with B over the length of A times the length of B. And this is something I remember learning about maybe 15 years ago when I started learning game programming. First of all, I discovered this equation, or this formula, and you know, it's just it's like it's just a way of multiplying vectors together, and you can calculate the angle between them. And once you know this, you can do any kind of field of view calculation using any programming language. So that's the formula. So this angle is going to be the inverse cosine of A dotted with B over the length of A. Oh, these shouldn't be called A and B in this thing here. This, in fact, for A is going to be B minus A, and then this is going to be A's forward vector. Okay, cool. So here we go. Here's the actual thing. Mathf.a cos vector 3 dot dot, the two sphere transform dot forward over the two sphere dot magnitude. This is going to be in, and let's convert it to degrees. So by going mathf dot rad 2 degrees. So that will convert it. And we maybe just print it out. Debug dot log theta. So that's going to be the angle, and let's print that as a string maybe. Plus theta. Save. Jumping back over here to Unity. Not this one. This one here. Here we go. Let's hit save. Oh, I don't need to save. Let's hit the play button now. Just going to print the angle. So there's the angle. Okay, it's fine. The angle. Let's take the sphere and move it around. So you can see the angle is 74. It's printing out down there in the bottom right hand corner. You can print the. I'll just move this all the way over here. Like if it's pretty much here, it's moving towards it. This is like a zombie game. This thing is just moving towards constantly. Zombie hordes. All right, you can see there that the angle is 90 degrees. 29 degrees, 0, and then this way is going to be 90 degrees. Oh yeah, it's 90 degrees because don't forget the forward vector for this is still pointing in this direction here. So then if I wanted to do my little field of view calculation, you would say that that's the angle. You could basically say if the angle is less than 45, so where are we, inside the field of view or outside the field of view? We can go debug.log inside FOV. Oh, I didn't call it angle, I call it theta. Outside the FOV, and maybe we'll just not update this guy's position again, so you know we can just see what it's going to do. So it's inside the field of view or outside the field of view. Here we go in Unity. Oh, wrong project. This project here. So you can see right now that the angle is 39 degrees. So down here it's printing inside field of view. And as I move the sphere around, it's now hopefully going to be outside the field of view. Why is it still saying inside? Oh yeah, because it's like not tracking it. It's now outside the field of view. So inside field of view, outside field of view, inside field of view, outside field of view. What would happen if we move the cube? Of course, if we rotate the cube, this thing will still work. So rotating the cube, it's inside field of view, outside field of view. You can see the switching between inside field of view and outside the field of view. So there you go. That's inside field of view, outside field of view. The calculating the distance then is going to do the second part of that, which is, you know, to check to see if the distance is less than a certain amount. Let's jump back over here to the vector testing. Okay, cool. I just wanted to show you. You see this line of code here? This being Unity, of course, this can be replaced with one line. All right, and the one line is this. Theta equals vector 3 dot angle between. So this will actually do that dot product thing and convert it to degrees for you and everything. So you can take the 2 sphere and the transform dot forward. I think it's actually called angle, not vector 3 dot angle between. There you go, vector 3 dot angle. So that will do basically this same line of code here. It does it all in one line, which is vector 3 dot angle, and that gives you the angle in degrees between two vectors. So let's have a little look. So again, inside the field of view, and as I rotate this guy over here, it goes outside the field of view, and it's inside the field of view, outside the field of view. So there we go, you guys. That's vectors. So I'll run through that again, okay? Just very briefly, I'll run through that again so you guys know what this stuff is all about. First of all, vectors represent sequences of numbers. In Unity, a vector is a vector 2 type or a vector 3 type, which has x, y, and z components on them. You can use vectors to store lots of different things, everything from positions, velocities, forces, acceleration, even colors can be stored in vectors. Then there are various mathematical operations which you can run on a vector. Operation number 1 is called adding vectors, and to add vectors together, you're adding the positions, you're adding the x's components of the vectors together with the y components of a vector. So subtract vectors, it's the same thing. You're subtracting the x's and subtracting the y's. Then we have this concept of the magnitude of a vector, which is basically the square root of the x component plus the x component to be squared plus the y component to be squared. And that's called the magnitude of a vector. Oh, I'm glad to hear that, Sean. I hope this is, you know, good for you and useful. It is kind of useful. It's basic, you know, kind of like vector maths. Yeah, the magnitude of a vector then being like the square root of the x component to be squared plus the y component to be squared. Normalizing a vector means dividing the x component of a vector by the length and dividing the y component of a vector to the length. And that gives you a vector which is always of magnitude 1. It's called a normal. What are normals used for? Normals are used all over the place. In Unity, if you are making a mesh, every vertex in the mesh has a normal, which says what direction is pointing out of the vertex in a mesh, and that is used for lighting calculations. No problem. I will paste the code into the Teams right now for you guys. And you know what I'll do as well? I'll actually put this into a Unity project, put it up on the repo somewhere. So that's adding subtractors, vectors, subtracting vectors, normalizing a vector, calculating the magnitude of a vector. The other thing then is you have that little formula for calculating the angle between two vectors, which allows you to do field of view type calculations. And anything else I can tell you about vectors? Maybe one last thing just to mention, okay? Because like this in terms of movement and position and velocity and stuff is, you know, that's kind of, I don't know what else to, you know, until we get into physics, and then physics as a whole. Oh, normalizing vector means making the vector of magnitude 1. And to normalize the vector, you divide the x component by the length and the y component by the length. Or you can also use the Unity APIs here for normalizing. It gives you a direction without having a magnitude. That's what you can think of normalizing a vector means. In Unity, the transform.forward, transform.right, and transform.up are all normalized. So they're all of magnitude 1. And then also vector 3.forward, vector 3.right, and vector 3.up are all normal vectors as well. So yeah, then we have this cool formula for getting the angle between two vectors, and you can also do it this way as well. Maybe I'll just mention one other thing to do with vectors, right? There is one other thing, which again, if you're interested in coding and this sort of computational way of approaching game development, which is what I kind of like do a lot of in my 4th year class, you will learn about this operation called a cross product as well. The cross product of vectors is a way of multiplying two vectors together, and instead of getting a single number, which is what you get with the dot product, because you're multiplying the x's and the y's together for the dot product, the cross product gives you back a third vector. And the cool thing about the cross product vector is it is always mutually perpendicular to the other two vectors. So how can I describe that? If this is your forward vector here, and this is my, say, other vector, if you get the cross product to those two vectors, you'll get this vector here, which points like mutually perpendicular to these things. This has like loads of applications. You can use it for calculating if a point is inside a triangle. You know, if you have the up vector and you have the right vector, you can cross them together and you're going to get the forward vector. You can use it to calculate normals in a vertex. It's called a cross product. In Unity, you do use the vector 3. I'll just give you a quick example of vector 3. Look at this, right? If you take this vector here, vector 3 will say A. Oh, here, I'll switch over to my screen. Apologies. I'll just show you what the cross product gives you. And then we'll finish our class, yeah? So here we go. So say there's vector A. Say vector A is equals to new vector 3. Say this is equals to the vector 0, 0, and 1. And say vector B is equals to the vector 0, 1, and 0. And of course, this works for all vectors. They don't have to be these, you know, nice clean vectors. You can do vector 3 C equals vector 3 dot cross A comma B. Here's a cool thing though with the cross product. Okay, let's print out vector C. Print out vector C like this. Guys, I am going to ask a question in the chat. I'm going to ask a question and see if you can figure it out. Like, obviously, you got A is 0, 0, 1, and you've got B is 0, 1, sorry, 0, 0, 1, 0. C, then, is C going to be 1, 0, 0, or is C going to be minus 1, 0, 0? I'll wait a second, see if anybody wants to make a suggestion in the chat. Like I say, when you do this cross product thing, you're going to get a vector which is mutually perpendicular to A and B. So one vector, perpendicular means it's a 90-degree angle. So we have 0, 0, 1 and we have 0, 1, 0. The only vector which is mutually, there's two vectors that are mutually perpendicular, 1, 0, 0, and the other one is minus 1, 0, 0. So which do we get? Do we get 1, 0, 0 or minus 1, 0, 0, 0? Minus 1, 0, 0. What do you think? I'll tell you what, let's run the program and see what happens. So I'm printing out vector 3 here. Let's run the code here and see what we get. Look at that. We get minus 1, 0, 0 when we multiply these two vectors together using the cross product. Just to show you that it actually depends. This is what you often hear this term, or maybe you hear this term later on if you want to go into the coding thing. You hear about the winding order of vertices, and this is what the winding order of vertices in a mesh determines which side of a mesh gets culled. You know, because if you think about it, if you got a mesh in a video game, which is representing, for example, a building, you only need to draw, if the person's outside the building, you only need to draw the face of the mesh, which is, you know, rendered towards the player. You don't need to draw the inside of the building, you only draw the outside of the building. And which side of a mesh gets drawn is determined by the order of the vertices in the mesh. It's called the winding order of the vertices. If they're clockwise, then they're drawn, one face is drawn and the other face is culled. And if the winding order is counterclockwise, then it's the opposite way around. And actually this cross product thing has the same concept of the winding order of vertices. So for this cross product thing here, if you were to switch this to be b comma a, you would get a vector that points in the opposite direction. You would get the vector 1, 0, 0. I mean, I'll just, you know, say that for like cross product, you know, maybe it's something that we might explore. Well, we do definitely explore a lot in fourth year. Guys, that is, I think I'm going to like finish up for there, you know. What to say? Let me put my camera on here. Oh, we had, let me see, do I want to even show you anything in fourth year? From fourth year before we finish? I will, for the hell of it. I'll show you something cool. Pathfinder. Yeah, let's save that. Let's save that to vectors. Yeah, I just wanted to say, you guys, listen, I have to go to final year project demos for an hour and a half at 2 p.m. I'll log on to the teams later, but like this is kind of like the last class for us. Next Thursday we have our lab test. No, lab test is next Thursday. Moved it forward to week 13. So the lab test is week 13, so it's next Thursday we'll have a lab test. And also your assignment is due then next Friday. Is that cool for everybody? Anything to say? You guys are all doing Git repos for your assignment, which is great. It makes it much easier for me. I'll give you guys a Google Docs form where you can submit the URL to your Git repos. Also, if you're familiar with the README file, so if you can put your documentation into a README file, which goes into the root of your repository, and I'll send you like some examples of how that looks. You know, you have the README file, the 17th. I don't really mind when we said the lab test was on the 13th, did we? Lab test, yes, it's on processing. There are lots of example lab tests on the course website from previous years. Let me check. I don't want to give you guys wrong information, and apologies for any confusion about this, because we did do a little bit of back and forth stuff here. Games Programming 2020-21. Let's just see what did we decide was the lab test and so on. Assignment is Thursday, 6th of April. January, February, March, April. Okay, so this is way out of date. 13th of May. The end of your lab test is the 13th of May. So the 13th of May is 2 weeks away. Check your email. It's to do with the assignment. Yeah, no problem, Ryan. Of course. How long is the test for? It'll be a 4-hour test, but it shouldn't take you 4 hours. It should take you an hour, I would say, max. Okay, you guys, so listen. End of your lab test then is Thursday the 13th of May. That's 2 weeks away. And then it's the end of that week we said was the 17th. Okay, is the assignment due? All right, that's fine. So like that's it for us. You know, this is week 13. It's the last class of the semester. So that means we have a break next week. And then the following week then everything is due. Yeah, awesome. That's fine. Cool. Thanks for the clarification, you guys there. And apologies for any confusion about that. So, yeah, this is kind of our last class then. Okay, I just wanted to say, because this is our last class, it has been my pleasure to teach you guys for the last year. It has been really like, the last year has been a big challenge for everybody, you know, like all this online teaching and everything. And I started out doing like things on bright space on my laptop, and then I got a new webcam, and then I learned how to use Teams, and now I'm learning how to use YouTube live streaming. So I think I'm kind of like learning and everything, and we're doing yoga every week. Anyway, it's been great crack, you guys, for the last year. Really looking forward to welcoming you guys to TU Dublin East Quad to, you know, maybe do some yoga and do some coding, more coding stuff in the future. Wish you guys happiness. Wish you guys a great summer and a very, you know, nice future, you know, learning all the cool stuff in TU Dublin, the best third level institute in the world as far as I'm concerned. And now we're going to move into the most beautiful campus that there's literally no campus in Ireland that is as like high tech, specced out as this place we're going to in September. So I don't teach you guys in second year. I'll teach you guys again in third year if you want to choose my subject, if you want to go down the coding route as opposed to like game design or asset creation or whatever. I hope you can think, like, my attitude is like literally, you know, you can learn anything. You know, coding is just like anyone can learn it. You know, there's no mystery to it. You just get better at it with practice. And you guys will get better at it just the more coding and stuff that you do. Just one thing about my subject in third year, it's a real computational way of thinking about games. So it's lots of creative coding, lots of choosing colors procedurally, lots of using various different kind of maths and linear algebra and quaternion rotations. In the second semester, it's autonomous agents, finite state machines, pathfinding, A-star algorithm, optimization. It's a computer science approach to game development. And I think you guys would really love it. I'll just conclude then by just like showing you the thing that we're kind of like working on at the moment. This is the last thing that we're doing in a game, and just to like give you a preview of what my course is like in third year. If you want to choose it, hopefully you guys will come and we can all do yoga together again. Let me see. I need to do the OBS thing. Switching over. Cool. So this is what we kind of be working on, you know. Oh man, so much cool stuff I could show you. Let's see. This is the avoidance, right? So this is kind of what we're working on right now. So got this little autonomous agent here, you see, and this little guy's doing a procedural animation, and it's just sort of perceive those obstacles, and then like it's basically swimming towards the target whilst also avoiding obstacles with a procedural animation and stuff, you know. And then, yay, it reaches the target whilst avoiding all those obstacles. And then just today we did this cool thing, which is using an algorithm called the A-star algorithm to calculate the lowest cost path between, it's the lowest cost path on a graph, and it's used to do pathfinding. It's basically how, it's basically how like the nav mesh works in Unity, but we coded our own version of it. So if I hit play here, actually I think I might need to edit the code slightly. Yeah, you can kind of see now what has actually happened is instead of doing the obstacle avoidance, what has happened is this little autonomous agent has calculated the shortest path between its starting position and the ending position. So that's what we're kind of like working on in game engines right now. We're kind of reaching the end of the class. And we'll have spent, you know, we spent maybe 3 or 4 weeks working on the entity component system. We made the Cytrans spiral generator, which I'll just show you that project. Again, this is all coming up in fourth year if you want to choose my subject. Open project. This might take a little while to load, and if it does, we'll just finish. And you know what? Pretty sure I have a build of it. Project ECS 2020 build. I'll show it to you running then, right? Instead of like, because it's taking a while to load up in Unity. I might have shown you this. I'm probably going to put this on itch because I think it's really cool. It's lots of examples that use, oh, it's opening the wrong window. Switch over to the thing. Display to, here we go. So it's just some examples of different things that use the entity component system in Unity. This is, I call this thing the Cytron spiral generator. You can do it in VR as well. It makes an infinite variety of like really cool, beautiful spirals. And then there's this example, which is the game of life using entity component system. This is a 500 by 500 game of life. So there's 25,000 things being updated every frame here. And then there's this beautiful thing here, which is the Boids example. And the Boids are implementing separation, cohesion, alignment, little autonomous agents doing all kinds of cool stuff. And still hopefully operating at like 90 frames per second, even though there's 28,000 entities being updated every frame in this scene, you know. So it's very cool to be able to do this kind of thing in Unity now, you know, where you have like massive numbers of things in your game and they're all being updated every frame. Like I say, in this scene here, there's 28,000 things being updated every frame. So using C# code, you know. So this is kind of what my subject is all about in 4th year. And like I say, it's a real deep dive into maths and all kinds of cool stuff. Listen, you guys, I'm going to finish there. It's been a blast. Have a great day, everybody. Hope to see you soon. Bye.